name is Edson. An embedded firmware engineer. I've been into the embedded world for the past 6 years, playing around with the embedded software, IoT, and other stuff. So today I'll be taking you through how to achieve multitasking with ARM CMSIS-RTOS. And just to highlight what we shall be looking into, I'll try to explain to you what is multitasking, have an overview of the ARM CMSIS-RTOS, and we shall look at different features that comes with the CMSIS-RTOS, things like the task management, inter-task communication, and also I'll highlight a few things about the software timers that comes with the RTOS. So again, we shall do a comparison of the CMSIS-RTOS versus other free RTOS or versus other RTOS APIs. And we shall see the advantages of using CMSIS-RTOS. And finally, shall close with a project, hands-on project, whereby we can define 2 tasks. As you can see from my video feed, I have my Nucleo board, Nucleo F446RE, and on my breadboard, I have 2 LEDs. We have one green and one that is blue, connected to pin PA5 and PA6. So the green wire is the ground. So we shall write firmware to make sure that we can blink the 2 LEDs in different frequencies. So we can have one blinking at after 1 second and have the other LED blinking after every 500 milliseconds. So multitasking is the capability of an operating system to execute multiple tasks simultaneously. So multitasking will help you like break down a complex task into several modules that you can define in the tasks that comes with the free RTOS. And then, for example, if you have a system that you want to create a system that will read the user's input, again, have a display like you want to view the logs, and also save the logs into the SD card. You may define 3 tasks. That's one complex task, but you can have 3 tasks that you can define separately. And then when you apply these on the RTOS, you can be able to define some things like the priorities for each task, so that you can give priority to the urgent event, like reading the user's input. And then when you're not reading the user's input, you can display it on the screen. So for example, let's look at this scenario. We have a smart home thermostat, whereby we want to monitor the temperature from a sensor. And then we have a fan that we want to control based on the temperature sensor values. Again, we want to show these values to a display. And we have the control that you can set the temperature that you want, and you can also set the speed of the fan. Again, you want to transmit these temperature data to a remote server or a remote platform, where you can also send commands to the device. So these are different tasks that you can define in your project. You can have one task specifically for reading the temperature sensor. We can have one task for controlling the fan, one for displaying the values, and one for the controlling, like the user's input and also the commands. And also one task for sending this data to a platform. So how you choose the priority depends on what is important. You can choose the fan, the task with the fan, to have high priority because maybe the temperature is so high and you want every time that the temperature goes beyond a certain value, you want to override every other task and then serve the fan task. I think that's something that has been covered by Zach about the preemption, whereby some tasks are dropped by the scheduler so that it can serve the high priority tasks. So the importance of adopting multitasking is one, we have the modularity. You are able to break down your codes into smaller manageable tasks. So you find that each task can handle a specific function or part of the system, making the code more modular and easier to maintain. So this gives you gives you an overview of what your task does, and in case you come into an error and you want to debug your code, you obviously know which task handles what. So you can easily go to that task and debug and get to correct your code. So another one is efficiency. So multitasking enables better utilization of the CPU by allowing it to switch between task efficiently. So this means that while one task is waiting for the maybe input-output operations, the CPU can execute other tasks. So thereby keeping the system busy and improving overall performance. So tasks that would otherwise block the system during the waiting period, like in the previous example, reading the temperature sensor, can run in parallel, reducing the idle time and maximizing resource use. So because of this idea of modularity, like I mentioned, it's very easy to maintain because assuming you have that system for the smart home, and maybe your fan is not running, it's very easy to debug that code because you already have a task defined to control the fan. Maybe the command is not coming, and you only have one task that is supposed to send the command to turn on the fan or turn off the fan. So it becomes very easy to maintain that code and also debug. So nothing is the real-time performance, and in system with real-time requirements, multitasking allows for prioritization of the task. So find that high priority task can preempt lower priority ones, ensuring that critical operations are executed within their deadlines. So this is a good example is when you're about to crash with a car. There are other things like the proximity sensor in your car, and what they sense an obstacle in front. Something like the airbag needs to be deployed very fast, and that becomes critical in part of it becomes critical to survival. So you must ensure that some tasks are very important, and you want to serve them as quick as possible because it could be deadly if you miss to do the action. Another thing, application of this is in the medical equipment, whereby you have to maybe supply oxygen if if the patient maybe stops breathing or something. So there could be a good task and a fast. I mean, there could be you could have a task that can that have a high priority to ensure that in case of something like oxygen runs out, you can directly go to another task, maybe to activate something else. So to achieve multitasking in the embedded system, today I'll be looking at CMSIS-RTOS. And what I can say about CMSIS first stands for Cortex Microcontroller Software Interface Standard. So this is a standard software framework developed by ARM to simplify the development of software for ARM Cortex-M microcontrollers. So this framework provides a consistent and portable interface for software components, and therefore it enables easier development and integration across different microcontrollers and development environments. And you can see that we have several components of the CMSIS. We have the CMSIS DSP. This is the digital signal processing functions that are optimized for ARM Cortex controllers. So in these, you'll find some of the mathematical functions, complex maths, and matrix operations. And things like the finite impulse response and infinite impulse response filters. Those are things that you need when you're working on digital signal processing. So you have the CMSIS-RTOS, which is our main focus today. And the CMSIS-RTOS defines a standard API for real-time operating systems to ensure that there is portability of RTOS applications. So these APIs comes with functions for task management, how to create a task, how to delete a task, how to suspend a task, and other things like synchronization, whereby we have things like the semaphores, the mutexes that deals with shared resources. And also we have inter-task communication, sending notifications or messages from one task to another. So we have the real-time kernel that the CMC sits on, and this could be the free RTOS. This could be the RTOS scale RTX. So you find that the CMC's RTOS has to sit on some real-time kernel. And well, I don't think, okay, so many people would say that CMC's RTOS, it's an RTOS by itself, but no, it's not. Has to rely on another RTOS. So for the functions that are provided in CMSIS RTOS, you'll find that how you set them, they'll be passed to the kernels that again will do the interpretation. So again, we have the CMSIS core. So the CMSIS core provide a standardized, provide a standardized interface for accessing the core features of the ARM Cortex microprocessor. So if either core peripheral access, whereby you want to access core peripherals like the NVIC, the C-stick, the debug trays, and other peripherals. So in here, in the CMSIS core, you'll find the definitions for the core registers and the bit fields. So we have also on the right side, the CMSIS SVD. And the CMSIS SVD provide a standardized format for describing the register and the memory layout of the microcontrollers. So further, there's a file, the XML files, that describe the peripherals register, things like the memory map, and you can also find other hardware details. So you find that third-party debuggers, when you want to debug your code, it's through the XML files or through the CMSIS SVD. So what is CMSIS-RTOS on its own? It is a standard CMSIS-RTOS API implementation interface with an existing real-time kernel. So, like I said, you have to the CMSIS-RTOS sits on another RTOS. So, for this diagram, you say that you have the application code. This is the user code that you have to write, and when you write this code, you may have your other functions. This is where you also define your task, And also this is where you can set some priorities for peripherals and other things. And when these are passed to the CMSIS-RTOS, you get that there's a translation that happens that again passed to the real-time kernel. Yeah. So some of the features of CMSIS-RTOS that we're going to look at, like I said, is the task management. And I'll explain how you can create a task, set the priority of a task, and then delete a task. So on the right side of these, you can see there's a code snippet whereby you have the what you need to write to completely have a working task in the CMSIS-RTOS. So the first variable is the OS thread ID, which in this case is the green LED handle. And this is unique, and it is used for identifying the task. Again, we need to set some attribute structure for the thread, things like the name of the thread, the stack size, and the priority. So I believe this has been covered by Zach. How you get to choose the stack size for your task. If you're dealing with data manipulation, you may need to have stack size enough to hold your local variables and such. So for the priorities, we have different levels of priority. We shall see these when we are setting up the STM32Cube. And for this case, you can see that the priority is set to normal and the stack size is set to 128 by 4. And we have the name of the task, the name of the attribute as a green LED. So this is just the attribute structure for the thread. So you need to create a prototype function that will hold the task definition. So we have this void green LED task and takes no argument. And down here, you'll find that we have defined the task. So we want that green LED task to have or to run the green LED. So it's always good to name your function to something relatable so that you don't get confused on which task was doing what. So assuming that you want to read the temperature values from a sensor, you may define that task as read temperature sensor. If you want to have a task to run the fan, because you can call it fan control, it becomes easy to locate. And if you have a huge number of lines of code, then it becomes hard if you don't get to name them well. So in user code begin RTOS threads here, this is how you create a thread. Use this function, OS thread, that takes 3 parameters. The first one is the task that you have defined here, the green LED task. And the second, it can be null, or you can pass a data structure. This could be for initialization. So you may define a structure that holds variables and you want to pass them to this task. You can pass them here. But for our case, we are not passing any initialization data to the task, so we shall have null. And then we have a point to the green LED attributes that we did. So to set the priority, the name, and also the stack size. So in the task, we have the green, we have the HAL GPIO toggle pin. You find that we have GPIO A. So this means that our green LED is connected to port A, pin number 5. And we have things like the OS delay, whereby you want to have some time. So for the OS delay, it's very important to use the OS delay here, other than the HAL delay. So the OS delay will translate this somewhat different to HAL delay. So when you use the OS delay, this will tell the scheduler that this task, you are pending it for maybe 1 second. So the scheduler will use that time to run another task. And finally here in the user code begin for, you can use the OS thread terminate to delete the task. So it's terminate or delete the task. So when you delete the task, then it will not run. Something else is the inter-task communication. We have the message queues, we have the semaphores, we have the mutex. So the idea of message queues is fast in, fast out. So you can send messages from one task to the other. And this is also kind of some of signals or notifications. Assuming that in the previous example that I showed here about the smart home, you can define a message queue that will handle the temperature value. That means we shall pass the temperature from the function that is reading and then send that temperature data to another task using the message queue. And then when you receive the message on the other side, we can get to decode the message, or maybe if it is the temperature sensor data, we can be able to do some if statements like if temperature is beyond this point, then turn on the phone. If turn on the fan, if it is less than this, then turn on the fan or turn off the phone. So how to create a message queue? It's very similar to the task because you see that we also have a unique ID, the OS message queue ID. And we also have to set the attributes for that. So just the name, the message Q1. And for adding the queue, this is how you create a new queue. So OS message queue new. We have the takes the 3 parameters. So the first parameter is the size of the data that you may want to transmit. And also the size of the unit 16. And finally, we pass the message attributes. That is the OS Q1. I mean the message Q1. So I had defined, I had prepared this. Whereby we have a default task, and we have a message that we have defined here. It's a unit 16, and I have this 123. So this is a message to be sent, and we also want to know the status if the message was sent or successfully or not. So inside this task, we have the forever running loop. So this is similar to a while loop. That means that task will never stop running until maybe you delete the task, or you can suspend the task for some minutes to make it stop running. So we have if you want to put some messages to the queue and send so that they can be received by the other function, this is how we do it. The OS message queue put, and then the message queue handle 1, this is the ID. So you are sending those messages into this handle, and then we attach the message. So in this case is 1, 2, 3. Then we have the OS wait forever. So you can take all the time you need to send this message. Okay, it may be a bit longer than maybe you expect, and you have enough time. If your system can have some time, or you don't have a definite time to set this message, then you can set this to wait forever until you send the message. So the status can be okay or fail. So when it's failed, you can do something else, like restart, sending a message again, or send some notification to another function telling you that this was unsuccessful and maybe you can do something else. So this is a part of where the message is being put, and we have the other side whereby we want to get the message. So for the message, to read the message, use the OS message get, QGet. You're getting from the message queue handle, and then you are receiving the message. We have no function, we have no parameters to this, and then we want to wait. You can wait forever for this message. So this is just to prepare your task that, yeah, you just receive the message when it's available. And you can see that I have an if statement here. If the received message is 123, remember in the previous section I sent 123, then you can blink the LED 10 times, or you can toggle the LED 10 times, maybe at a delay of 100 milliseconds. Doesn't have necessarily to be an LED, it can be something else. You can send a message that I received this, or you can now use this function or task to log data to your SD card, or even maybe transmit this to the server. So for the semaphores and mutex, these will be covered in the next sections. So again, the CMSIS-RTOS comes with the software timers, whereby you can have periodic timers that can run some task periodically. If you want to, maybe your system has to know that your system is on. You may have one LED, and just to notify you that it's still functional, you can keep blinking that LED after every 2 seconds or after 3 seconds, depending on what you need. So this is why you can use the periodic timers to do that. You can also use the periodic timers to send data to the serial. Think of any task that you want to run after every some specific seconds. So you can also create some delays by using some of the global variables. Since that when you have the callback function called, you can set that flag to 1, and then you'll have achieved a delay of what you want. So again, it's similar how you create a timer. And you can see that we have the OS timer ID. Again, very unique for identifying. And we also have to set the attributes. You can see the name is the green LED timer. And then we have to set this callback. So you have to define a callback that will be called after the time elapses. So in here, this is the function prototype, and it's defined down here. So inside the function call or callback, you can have, just as explained, you can have a task. So how to go to create a timer? Use the OS timer new. Then you have to set the callback that will be called, and the timer can be one shot or periodic. So this is set to OS timer periodic, and takes no initial configuration data. And then you have a pointer to the green LED task. And if you want to stop the timer, you also have functions to do that. You can use the OS timer stop, and then you pass the handle. And you have the OS timer delete if you want to kind of discuss the whole timer. So you realize that all these things comes with a unique ID. So that means you can have different timers. You can have more than one queue handle, or message handle. You can have more than one task depending on your system. So if we do a comparison of the features of different RTOS, you can see that for task creation, the API used to create a task in CMSIS-RTOS is different from the free RTOS, different from the KRTX and the Microcontrollers OS and the chibi. So I haven't dealt with the last three OS, but you can see that there is a difference in the methods or the APIs. So we have the task deletion. In CMSIS-RTOS, we have the OS thread terminate, whereas in free RTOS, we have the task delete. So same as the task suspension, resume, you can suspend, or this is the OS thread suspend. So this is v-task suspend or v-task resume. So again, they all use the time slicing. And you can see that the scheduling algorithm, all of them are similar. It's priority based by default. For free RTOS, it's configurable. For KRTX is by default priority based. And yeah, for the intertask communication, we have the message queues. So this is how you create a message queue in CMSIS-RTOS, the OS message queue create. And for the free RTOS, we have the XQ create. So you can see that we have different naming conventions for these functions. So advantages of using RTOS. One is it is optimized for ARM Cortex-M architecture. So the CMSIS-RTOS is optimized specifically for ARM Cortex processors, and this leads to better performance and more efficient use of system resources compared to other generic RTOSs. So standardization, I find that the CMSIS-RTOS provide a standardized API that is consistent and also compatible across different real-time operating systems. So this makes it easier to port applications between different RTOS to implement and also reduce the learning curve for developers. So we have ease of integration, and it is designed to integrate seamlessly with with ARM Cortex-M microcontrollers and the other CMSIS components. And they find that this integration simplifies development and allows for more efficient use of microcontroller features. So due to the ease of integration and how it's standardized, then you have reduced development time for your project. So again, we have the task prioritization, and you find that each task comes with a priority that you can set, and this makes it possible to achieve real-time manipulation where time constraint is very important. So you also have comprehensive documentation and support. So yeah, it's, how do I put this? The CMSIS-RTOS benefits from extensive documentation and community support provided by ARM and its ecosystem. So this helps developers troubleshoot issues more efficiently and leverage a wealth of resources. So again, you have broad support from the CMSIS-RTOS vendors, and offers a wide range of options and flexibilities in choosing an tool that best fits the project. So enhanced portability, like I mentioned, it's easier to port from one tool to another. And finally, to our hands-on project, we're going to set a project to blink the two LED at different frequency. And yeah, allow me to shift to STM IDE. I'm going to create a new STM32 project. So select the board that I'm using, Nucleo F446RE. And then I can call these CMSIS-RTOS multitasking. So this will take a minute. Yeah, here we are. So I'll not change a lot the default configuration. Maybe I just need to deactivate the UART. And then, as you can see by default, the green LED pin P5. By default, the Nucleo board comes with an onboard LED, but I'm going to have mine external, and it's connected to pin P5. So I've also connected a blue LED to pin P6. So maybe I can have this as blue LED. Yep. So maybe from my breadboard, let me just switch these to make sure we have as defined. So we can have, then we go to middleware, and then we have these FreeRTOS. So in the interface, we have the CMSIS version 1 and version 2. So version 2 is the updated version of the for the CMSIS version. So you might want to work with version 2. And if you look here, we have things like mutexes, we have events, we have the task and queues, we have the timers and semaphores. And yeah, for today, we are going to work with the task. And by default, the STM32 queue perspective have one task by default. So I'm going to click on this task, and you'll see that we have the task name, the default task. We can change this to green LED. And then we have different priority levels that you can choose. So you have the priority low, priority, the lowest priority real-time 7. So we have so many priority levels that we can choose. But I'll go with normal or below normal. And here you can select the stack size. So by default, I'll leave it at 128. So the entry function, we can also rename this to be green LED underscore task. And then we can leave the rest as by default. So yeah, let's generate the code. Yeah, so we have this warning. When RTOS is used, it is strongly recommended to use the HAL time base source other than SysTick. So the HAL time base source can be changed from the pinout tab under sys. So The reason why we got that warning is that the CMSIS-RTOS uses the SysTick timer. So we can choose, we have to choose another time base for operations. So you can select that under system core, and under sys, you can select another timer, like timer 6. And then let's generate the code again. So it says that the new, so use new implement. Okay, so let me just go back there and select that. I cannot find it. Just a second. Just locate that. So yeah, let me about this. Then generate the code. And then you'll find that we have the thread, I mean the ID for our task. We have the green LED handle. And then you have the attributes for that. We have set the name to be green LED. We have the 128 by 4 stack size, and then the priority is below normal. So again, since we set the task in the CubeMX perspective, this has also been generated for us, the LED task. And this is where we're coming to create the LED task now. So we find that you have the OS thread new, and we have to pass the task, which is the green LED task, no initial data that you want to pass, and then we have the green LED attributes. So our function definition perspective. So we can define.
Hey, Edison, we lost you there for a second. Can you go back maybe 15, 30 seconds? You were talking about the function definition.
Oh, function. Okay, sorry about that. Can you still hear me?
Yep.
Okay. So coming back to the function definition, this is the task. Remember that we had a task called the green LED task. And the function comes with a for loop inside. You can change this to a while loop as long as you can have a while one and it'll still work, because this is something that you want to keep running every time. So this is where you want to define what you want to run. And if you have some of the initialization parameters, you can declare them here. Assuming you want to have some static variables that you want to set first before you run what is inside the function. So let us go up there and create another task. So going to come here to user code begin private variables. So we can have OS thread ID, OS thread ID, and then we can call it blue LED handle. And then we want to set the attributes. So just allow me to copy and paste these here. And yeah, you can choose to keep the priority to be below normal, or you can choose the priority level above normal. And then the stack size, we shall leave it at 128 by 4, and we can change this to below LED. So again, we need to have a task. So let's have this task can have as below LED task, and we have this void argument, and we are going to define this in user code begin for. And inside here we shall have a for loop. Yep, and we can have an OS delay of 500 milliseconds. So this is the task definition. So we have not created the task yet. So we need to come here to user code begin RTOS threads. So someone may use thread and task interchangeably. So we can have the below. Let me pick it up from here. Is equals to OS thread new, and the function that we want to call is this one, and the argument we have null, and the attributes we want to pass the green LED attribute. No, we have to change this to blue. So blue LED attributes. Yep. That's it. So again, for you to start running the task, you must call the OS kernel start, or you start the scheduler. So let's have some codes in this task. So for the green LED is connected to pin PA5. So we can have HAL GPIO toggle pin. So GPIO A. This is from port A, and this is from pin 5. And a similar thing, we have this, but we're going to change this to pin P6. This is the blue LED connected to pin P6. It's always good to comment your code. Let me also have this pin P5, and this should be green. So let's build a code. Seems that we have an error, and let's see what that is. Argument 3. So yeah, forgot that. Yeah, code have no errors. So let's run this. So you can see that we have the blue LED, like I said, is blinking after the blue LED is here, blinking after every 500 milliseconds. And for this one, it's running after every 1 millisecond. So let me increase that to 1 second and download. So you'll see that the two LEDs will blink at different frequencies. You can see. So this is after every 1 second, and this is after every 500 milliseconds. So let me show you the importance of calling these OS kernel. So I'm going to comment these and download the code. And you'll see that nothing is going to run because you have not started the scheduler, which is supposed to allocate some time for those tasks and then do the scheduling and context switching. So what happens is that you cannot put your code in the while loop when you are using the FreeRTOS, because when you start the kernel, the code does not come to this point. So we can have, let me just have something like a function here or an operation. And just build this. I'm going to enter into debug mode just to show you that the function or the while loop or any code that you put in the while loop will not be run. So I'm going to have a breaking point there. And you can see that, yeah, it's not stopping because whenever you start the scheduler, then it will start running the task. So much more to be done much more to be done on FreeRTOS. But I hope that you got the idea of how to create a task. We shall cover more like things like messages in more sessions to come. So yeah, so that's all for today.